In this video, we're going to explore, well, quite a few fascinating topics. We'll start with quantum computing itself, then move on to classical versus quantum bits, also known as qubits. We'll look into quantum superposition and entanglement, quantum gates and circuits, and how quantum computers actually solve problems. We'll also talk about different types of quantum computers, real-world applications, challenges and limitations, and finally, the future of quantum computing. Let's get the introduction first. Quantum computing is not science fiction. It's real, it's here, and honestly, it's changing the future of technology. In this video, we'll break down exactly how a quantum computer works, what makes it different from classical computers, and how it's being used in areas like AI, cryptography, and materials science. Now that we have got the introduction about quantum computers, let's compare them with traditional ones. Traditional computers use bits, binary digits that can be 0 or 1. Everything from web browsing to AI models runs on combinations of these bits. Quantum computers use qubits. A qubit can be in a state of 0, 1, or both at the same time, a phenomenon called superposition. Mathematically, a classical bit is either 0, which we write as 0, or 1, written as 1. A qubit, on the other hand, is written as psi equals alpha times 0, plus beta times 1, where alpha and beta are complex numbers, and the sum of the squares of their magnitudes equals 1. That's the probability rule. Now comes a question. What is superposition and entanglement? Superposition allows qubits to represent multiple possibilities simultaneously. This gives quantum computers an exponential advantage in certain calculations. Entanglement is a quantum phenomenon where two or more qubits become linked. Measuring one qubit instantly reveals information about the other, even if separated by large distances. For example, if qubit A and B are entangled, and qubit A is measured as 0, qubit B will instantly collapse to 1, and vice versa. This allows qubits to compute together in complex, nonlinear ways that classical computers just can't match. Now, let's hop onto quantum gates and circuits. Just like classical computers use logic gates, and not quantum computers use quantum gates to manipulate qubits. So let's talk about some examples of quantum gates. The Hadamard gate, often called H, creates superposition. Then there's the Poly-X gate, which is kind of like the quantum version of a NOT gate. The C-NOT gate is used to entangle qubits. And finally, we have the T and S gates, which are phase shift operations. Quantum circuits are built by applying these gates in sequence. The output isn't a deterministic value, it's actually a probability distribution. You run the same circuit thousands of times and, well, you analyze the output statistically. But how do quantum computers solve problems? Well, quantum computers are not faster at everything. They really shine when it comes to solving problems where classical computers scale poorly, like optimization, simulation, or cryptography. Alright, let's talk about some example algorithms that are really changing the game in quantum computing. First up, there's Shor's algorithm, which can crack large number factoring exponentially faster. Basically, it could break RSA encryption, which is kind of a big deal. Then we've got Grover's algorithm, which is all about speeding up unstructured search problems. And there's also the quantum approximate optimization algorithm, or QAOA, which helps solve tricky combinatorial problems like route planning. Pretty impressive stuff, right? So these algorithms actually use interference and entanglement to amplify the correct answers and, suppress the incorrect ones. It's a bit mind-bending, but that's what makes quantum computing so powerful. Now let's see the types of quantum computers out there. There are several approaches to building quantum computers. First, we have superconducting qubits, which are used by companies like Google and IBM. Then, there are trapped ion qubits, and those are used by IonQ. We also have photonic quantum computers, which use light for computing. And finally, topological qubits. They're still theoretical, but honestly, they're really promising for fault tolerance. It's quite a race to see which approach will win out. So each approach comes with its own set of trade-offs. When it comes to things like coherence, time, error rates, and scalability, there just isn't a perfect solution yet. But you might be wondering, what are the real-world applications that quantum computing is actually expected to revolutionize? Well, quantum computing is expected to make a huge impact in several areas. For instance, in cryptography, it could either break or actually strengthen encryption. In drug discovery, it could help simulate molecular interactions in ways we've never seen before. In materials science, it might enable us to design entirely new superconductors or batteries. In finance, it's all about optimizing portfolios and managing risk more efficiently. And not to forget, in artificial intelligence, quantum machine learning models could bring about new breakthroughs in pattern recognition. These applications, well, they're still pretty experimental at this stage, but honestly, they're progressing really fast. Quantum computing has, many advantages. But what are the challenges and limitations of them? Well, quantum computers are actually pretty fragile. Qubits tend to decohere quickly due to environmental noise. They require cryogenic cooling that's close to absolute zero, error correction, and thousands of qubits to run large-scale useful programs. So, as of now, quantum advantage, where quantum computers actually outperform classical ones, has only been achieved in some, really specific tasks. It's not something we've seen happen broadly just yet. Let's not focus on those disadvantages for now, but instead, let's hop straight into the future of quantum computing. Companies like Google, IBM, Microsoft, and a whole bunch of startups are actually investing billions into this field. Right now, we are in what's called the noisy intermediate scale quantum, or NISQ, era. But we're moving toward fault-tolerant universal quantum computing, and honestly, that could happen in the next 10 to 20 years. If you enjoyed this explanation, please like and subscribe for more real science. No hype, just the facts. And hey, drop your questions below. We might answer them in a future video. Bye.